Okay, so today we are going to be learning about eccentricity and how it relates to ellipses. So, what is the definition of eccentricity? Eccentricity is a measure of how much the conic section, which we'll be talking about ellipses, deviates from being circular. We see this from there are two formulas from eccentricity, but they are both the same. They're both equal. There's only one difference I will explain a little later. One is E equals big F over big A, and the other, which is the one we'll be using, and we have E equals C over A. Eccentricity is always going to be between 0 and 1. This is because, now here we see that F is the distance between the two foci of an ellipse, and big A is the whole major axis of the ellipse. So if we have a big F, like around this size, it's going to be close to 1. And if we have a small f, the division between f and a is going to be closer to 0. So it's always going to be between 0 and 1. So why are these two equations equal? So what is C? C is the distance between the center and the focus. And little a is this distance between the center and a vertex. So here we see that little a, that big A is actually 2 times A, right? And F is 2 times C. So it ends up just being the same equation. Like it would end up being 2C over 2A, which just ends up being the same thing. So it doesn't matter which one we use, but in this one we'll be using big F over big A. So when talking about ellipses, we always think about planets, how planets are ellipses. This is stated by Johann Kepler's planetary orbits. So we will be talking about how we can draw Earth's orbit by using eccentricity, and we can do it without even looking, right? So by looking it up, we can find and then just look it up in Google, or in my case, we found it in a document. We see that Earth's eccentricity is very low. It's very close to 0, as we can see, 0.02. Now, concerning A, you can just not assume, but use any value of A. Since it's a proportion, it's going to end up proportional to Earth's actual orbit. Even though it doesn't have to be a huge number, it will still be proportional to Earth's orbit. So we're actually going to draw Earth's orbit in a sheet of paper. It's going to be exactly proportional to the real Earth's orbit, right? So I chose that the major axis, big A, would be 20 centimeters. So then we basically already have what big F is, which just multiply A times both sides. F equals E times A, so 20 times 0.02 is 0.4 centimeters. I forgot that right here. So how will we actually draw this ellipse? So what we do is as follows. We know that when drawing an ellipse is when you have two foci, right? And the distance and the sum between the two lengths, between the two legs, is always going to be a constant, right? Well, in this case, in all cases really, both legs are going to give us always the major axis, which we already know. So we can divide by 2, and we know that x and y here that we chose is actually 10. So what we only need to do is grab 2 push pins, plug them in here, and 10 centimeters here, 10 centimeters here, and go around. However, we don't have to do 2 knots. We can just do one by adding this value of F right here. And with this whole one, we just need 1 knot with a string of a length of 20.4 centimeters, because we have X and Y. X plus Y would be A, right? And then we have F, which is 0.4. So by using this length of a string, we would be able to draw the whole ellipse correctly. So we found that A plus F equals 20.4. So here what I did was, so both this side right here is 10.2 and 10.2, and I did a little knot. And we can find, with this length right here, we can draw an ellipse proportional to Earth's orbit. Right, so here we go. Alright, so we're going to use 2 push pins at the focuses along with our string that we found. So what we're going to do, we're going to grab a piece of cardboard to plug the push pins in. So we're just gonna...
1 second, you only have 9 minutes, okay? Left of memory. Is that enough?
Yeah, that's enough.
Right, cut.
So we put this push pins in. We know that F is 0.4, so this is 0.4, right? Now we put the push pins in. Wow, it's very small. There you go. There you go. And we attach the string. We grab a pen. And we simply draw the ellipse. Whoops. Let's try that. There we go. It's a kind of messy because of the cardboard, but you get the point. So, we have F right here. And we have the center right here, right? And we have, everything that an ellipse has, right? You have the major axis, which is 20 centimeters, and that is the ellipse. So what can we say about this ellipse? We can say that it's very circular, so it has very low eccentricity, and that's what we find. We can also another type of ellipse that is represented in the real world or the real universe is Halley's Comet. Now Halley's Comet actually has a much bigger eccentricity than Earth's. It's 0.97, so very close to 1. So we're going to have a more oval-shaped ellipse. So using the same procedures, we find that F is 39.4, and that the length of our string, right here, the same procedure that we use right here, A plus F, is going to be 39.4. So a string, both sides, both lengths, the whole string is 39.4 centimeters. We grab cardboard, put the push pins in. Same procedure as last time. We know that the distance F right here is going to be 19.4 centimeters, so we measure that. And we put this together right here. As you can see, it's going to be very, very oval shaped. We can fill this in a little bit. All right, so that is the ellipse of Halley's Comet. So we see, a much bigger eccentricity gives us a much more oval-shaped ellipse. So that is the project, and that's it.